That is section 8.4, derivatives of log functions. We did the derivative if f of x was equal to b to the x. We did the derivative by first principles initially, and we ended up with an expression that looks like that b of x times the limit as h goes to 0 of b to the h minus 1 over h. And what we discovered was that limit, if you had the letter e, that limit equaled 1, and so that's why the derivative of e to the x was e to the x. But all these other bases, we found that if you have y equals b to the x, that the derivative of it was b to the x, but then it turned out to be multiplied by ln of b, which is what that limit turns out to give you. That is a useful limit, or a useful derivative, obviously, in case you have, y equals 5 to the x, and somebody says, what's the derivative? Well, you can say it's 5 to the x times ln of 5, so it's like a little correction term there. It turns out that also works in logs, that if you have a natural log, that obviously we know from the previous section that natural log, if we take the derivative, it's 1 over x. But what happens if I have log base 5 of x? It turns out the derivative still starts off with a 1 over x, but you end up with this ln of 5 term, again, natural log of the base, and this time it turns out to be in the denominator. In the general sense, and for any base, log base b of x, the derivative is going to be 1 over x times the natural log of b. And when you use the base e, obviously that term goes away because natural log of e is just 1, and that's why the derivative, as we saw up here, is this one. If you're really interested in the proof of that, I'm not going to hold you responsible for proving why this is the case. This is on your formula sheet. But you can take a look. It's right around page 379 of your book. They kind of do a relatively easy proof of that one just to show you where it comes from. Let's take a look at a couple of quick derivatives here. If we have y equals 3 to the x to the 4, and I want to find the derivative of this, I start off by saying, well, it's exponential. The variable's in the exponent, so I have 3x to the 4 as my first piece. Then I have, since the base wasn't e, I have this ln of 3 term in there. And then I have to say times the derivative of the exponent there, which is 4x cubed. And so that would be the derivative of that strange function there. Now, if we have something like this, y equals log base 10 of 3x plus 1 to the power of 4. First of all, before you jump right in, I would bring that exponent out front to say it's 4 times log base 10 of 3x plus 1. Saves you a bunch of chain rule stuff that's unnecessary later anyway. So my derivative is going to be 4 times, now any log in this format is going to give me 1 over what's inside there. But this wasn't base e, it was base 10, so I have times natural log of 10. And then I have to say times the derivative of 3x plus 1, which is times 3. So I could write that slightly nicer to say this is 12 over ln 10 times 3x plus 1, but really not a lot of simplifying goes on with that one because there's nothing to cancel out.